Well, hello everybody, and welcome to this fourth webinar in the Meet the Researchers series with a focus on water. These webinars have been organised by our colleagues in the advancement team at the University of Leeds in association with Water at Leeds. And my name is Martin Tillotson, and I'm one of the directors of Water at Leeds, and it's my pleasure to act as your host for today's webinar. Now we'll get going with the webinar in a few moments, but before we start, just three announcements if I can. The first announcement is that, like with the other webinars, this webinar is being recorded, and the recording will be posted onto the advancement team's YouTube channel later on today. So if you're unable to stay for the entire webinar, or indeed if you would like to recap in the future, or if you would like to see any of the other webinars that have been recorded, then just head over to the YouTube channel and you'll be able to find them there. The second announcement is that we have a Q&A session following the presentation today, and we encourage you all to ask questions. You can ask questions either at the end of the presentation or during the presentation. And if you'd like to do that, then just hit the Q&A button at the bottom of the screen, type in your question, press enter, and it will appear along with everybody else's questions. If you see any questions on there that have already been asked and that you're interested in knowing the answers to, then you can also upvote those questions and they will come to the top of the list when we're going through them later on. And then the final announcement is that if you have any accessibility needs, we have closed captioning available on the webinar. And again, there should be a button at the bottom of the screen that you can click on if you wish to take advantage of that function. Right, so those of you that have been with us over the last 3 weeks will have noticed that we began this webinar series by having a look at some of the most pressing water issues right around the world. And those water issues were at a variety of different scales, in a variety of different locations, and affected different groups of people or different areas of the environment. One of the things that Professor Anna Medee did at the very beginning was she highlighted some of the top questions and some of the 6 or so themes that she was able to identify as being the most pressing water challenges around the world. So that was in the first week. And what we did then over the next 2 weeks, and indeed what we're going to be doing today, is we're going to just start to drill down a little bit into some of the detail around some of those challenges. So you may recall that 2 weeks ago, my colleague in the School of Civil Engineering, Dr. Paul Hutchings, talked about some of the social issues around water and water management, and particular focusing upon the effects of poor sanitation and water availability for sanitation, which is a huge issue affecting some 4 billion people around the world. And then last week, my colleague in the School of Earth and Environment, Professor Julia Martin Ortega, started to discuss some of the economic issues around water management, particularly focusing on peatlands and some of the economic issues around whether to invest to improve the condition of peatlands, given some of the economic imperatives that peatlands bring. So that brings us on to today's presentation. And this week we're focusing on some more of the environmental issues of water. And particularly we're going to take a closer look at what we call the third pole. Now you may not have heard of the third pole, but it is in fact the third most important resource for fresh water on the planet. Following the North Pole and the South Pole. The third pole is actually a massive area of southern and southeast Asia, covering some 1.6 million square miles, and is home to some 220 million inhabitants. So the third pole actually takes in some areas of the world that you would be very familiar with, such as the Himalayas, the Hindu Kush, and the Tibetan Plateau, but also brings in the Pamirs and the Tian Shan Mountains. So an incredibly diverse and vast area. And in fact, there are 10 major rivers involved in the third pole. Why is the third pole important? Well, as I've already alluded to, it is a major source of fresh water in the world. But moreover, that source of that reservoir, that source of fresh water is under threat because of the impacts of anthropogenic effects, but also of climate change. And one of the things that we find is that this area of the world is disproportionately affected by climate change, and particularly by global warming, and that many of these areas that would be considered to be permafrost or ice are in fact starting to melt. And so that threatens, of course, it threatens the habitats and the environment in these regions, but it also puts at risk the population. And of course, with meltwater, brings the risk of flooding as well. And as we've seen all too tragically and recently in low-lying areas like Bangladesh, which is downstream from this area, we see very significant flooding, particularly when the meltwaters combine with a worse monsoon season at certain times of year. And in fact, in Bangladesh, some 7.2 million people were directly affected by the impacts of the flooding in 2022. So without further ado, what I'd like to do now is to introduce you to our speaker for this evening, Professor Duncan Quincey. Duncan is a professor of glaciology in the School of Geography here at the University of Leeds. And he's going to talk to us about some of the issues that water management in the third pole brings. Duncan, I should just finally add, is a contemporary glaciologist, so his interests really are focused around water management and the impacts of climate and climate change on the third pole. So without further ado, if I can, Duncan, I would like to hand over to you and look forward to listening to your presentation today. Thank you.
That's wonderful. Thanks, Martin. That was an excellent introduction, actually, and you've done a good job of expressing the importance of the third pole, which I think for me, really, it comes down to this lovely intersection between the people and the environment here. Perhaps in contrast to the Arctic and the Antarctic, where the environmental changes are a little bit more disconnected to the impact that they have on people. But it's very stark here in the third pole, and I think that's why this is such a fascinating region to be able to study. So I'm going to talk to you a little bit about how climate is impacting on the ice reservoir that Martin talked about here. And I'd like to start with a bit of an introduction about the people, the climate, the ice and the water, just putting a little bit more flesh on those bones that Martin was talking about. And then really the main emphasis of the talk is two outstanding research questions that myself and my PhD student, Alex Scoffield, who unfortunately she can't be with us to present her work herself, but we're actively trying to address these two questions at the moment. And the first revolves around how warm the ice is in this region. And that was addressed by the Everdrill project, which I'll just briefly introduce you to and show you the key result from. And then I'll talk to you about our spring fieldwork plans that really revolves around Alex's PhD and the sorts of research questions that she's trying to answer. I think at the end, we'll bring it back round to the people again and just emphasize the work that we're doing with the communities in which we're working, and to be able to disseminate some of the findings from the work that we've been doing. And I'll just summarize the key points before we move into some questions and discussion at the end. So let's start off then with the Himalayan region itself, the people, the climate, the ice and the water. And so I guess there may be people on the call who are even living in this region right now, but if you're not familiar with the Himalaya, well, for a start, it's a very dramatic landscape. You can see there the image on the left-hand side. We've got these high mountains which are adorned by ice and snow, and that ice and snow frequently feeds down into the low elevation areas, and the water is used by villages like the one you can see there on the left-hand side, which has been cut into the mountain slope. And so these people are relying on water on a daily basis that comes from the snow and from the glacier ice for irrigation and for sanitation, for hydropower development, for example, on a small scale, even village by village scale at times. And the top right there, you can see a direct connection between a villager in Pakistan there. He's actually standing on a debris-covered glacier, and he's digging an irrigation channel into that glacier that taps into the meltwater and pipes that water then down into the village into storage tanks that they can use. And you can see the ice in the background of that image there that shows that he's standing actually on a glacial mass. And then at the bottom, some young gents that are using the water that's come from these snowfields to do the daily washing activities, that can also be then used for sanitation and for irrigation and so on. So a direct connection here between the people and the environmental changes that we see. And if you think about the resilience of these people to these changes, then it's a really interesting web of different factors which I think feed into their ability to be able to adapt to these environmental changes. And I think perhaps people like me often forget that people of these regions have been adapting to environmental challenges for many centuries. And so, although at the moment, this challenge that we have around climate change and the way that that's impacting these landscapes is very stark, the people of these regions are well equipped with many of the tools that they need to be able to be resilient to these changes and to be able to adapt. And so our part is really on this physical science element. It's about providing some of the quantitative evidence about how glaciers have changed over the last 30, 40, 50 years. And then the sorts of rates of change that we can expect to see going forwards. In terms of climate then, if we look at this slide here, there's quite a lot of data on here, but let's just start at the top left. And you can see some climatic projections for the near future. That's for the period 2036 to 2065. And the near future change that we can expect to see in the monsoon period, that's what's shown here, JJAS stands for June, July, August, September. For the main bulk of the Himalayan range, which is in that middle box HK, H2, then we might expect to see in that sort of time period a 1 to 2 degree change in temperature. So that's near future, and that's under a fairly moderate emissions scenario. But if we look then at panel B and we look at RCP 8.5, which is quite an extreme emissions scenario, but one which we're doing a good job of actually meeting at the moment, unfortunately. You can see the sorts of temperature changes that we're anticipating here could be up to 2 to 3 degrees quite comfortably, even in that period, which is up to 2065. And in both scenarios, the lower two panels in terms of precipitation, for the same monsoon period, which is critical for the ice in this region, we can expect to see an increase in precipitation. So we can expect to see a warmer region, and we can expect to see a wetter region. And the panels on the right-hand side of this slide really tell us that these sorts of changes are going to be enhanced once you get to high elevation. So you can see on the y-axis, you've got the elevation of the different weather stations that have been observing temperature changes within this region. And the darkest dots, is it a dark red perhaps? I think it'll be coming through on your screen. You can see the fastest rates of change, the fastest rates of temperature change are once we get into those high elevation bands. And that's exactly where our glaciers are sitting. So there's this phenomenon called elevation dependent warming. And it simply says that the higher elevations are going to be hit harder and they're going to be hit faster in terms of these climatic changes than the low elevation valleys, for example. So this has quite stark meaning for the ice, which is in these high elevation zones. And the data that we have show us that over the observational period, which is generally the satellite era, so about the last 30 to 40 years, these glaciers have been losing mass at an unprecedented rate. On the left-hand side of this slide, you can see the data that we have on surface elevation changes for the glaciers throughout this third pole region. That's this arc that you can see going from the middle of the image down towards the south and round to the east. And you can see that although there's some blue colours up in the Pamirs and the Karakoram, which we understand quite well, these glaciers have been quite stable for the last few decades. For the vast majority of the rest of the glaciers, we see these red colours that indicate that the glaciers have been lowering at a rate of about 0.5 metre per year, something of that sort of order, for several decades. And if you start to stack that up, that's actually a huge amount of ice loss. And hand in hand with that, if you look at the image on the right-hand side of the screen, this is to do with how the glaciers have responded in terms of their flow rates, their velocity. And we can see again, the red colours and the orange colours indicating that the glaciers are slowing down, they're decelerating. Well, glaciers are supposed to flow when they're healthy and when they're nourished. You get this consistent speed, which might have some small perturbations, but we don't expect to see a 10% slowdown, for example. So these glaciers are slowing down and they're losing mass, and they're doing that at an accelerating rate. And the latest data that we have, that's at the bottom there, it indicates that for the whole world, 8% of the global glacier mass loss can be accounted for this region. But perhaps most importantly, when we see the accelerated change, when we see the rate of change, then the High Mountain Asia region, which encapsulates the third pole, actually accounts for 19% of that increased rate of mass loss. So this region is already being hit harder and faster than most. If we want then to be able to project forward, we can use those past measurements as an indication, and we can prime our numerical models based on those data, as long as we can accurately simulate what's happened in the past, to be able to say something about what's going to happen in the future. And the point that we're at the moment in this region is one where we're not actually quite sure what the most robust analysis going forward is going to be. And the main reason for that is the fact that we don't really have many field data with which to properly parameterize our models. And you can see on the left-hand side of this slide, there's 3 different projections for volumetric loss for the glaciers in the Everest region of Nepal by 3 different groups. At the top, a projection of 70 to 99% volume loss by 2100 for the glaciers in the Everest region. In the middle, a projection of 50% volume loss by 2100. And at the bottom, our own projection, the group that I work with, 8 to 10% volume loss by 2100. So some very extreme scenarios, a big range in our projections, and we're the people that are supposed to know about this sort of thing. So the problem comes in that we have very little actual field data to be able to properly parameterize these models. And that's where the uncertainty comes in. And that's really what Alex and myself and others in the School of Geography here in the university are working towards. We want to reduce those uncertainty bounds and come up with something which is much more robust. And so there's 2 key areas where we don't have enough information. The first is what is going on inside the glaciers. We have very little internal data because these glaciers are at about 5,000 meters. And it's very difficult even just to get up there. Never mind have some instrumentation or some machinery, some equipment that's actually going to work without failing at those sorts of extreme altitudes. And the only real internal data that we have to rely on come from almost 50 years ago. That Japanese expedition you can see in the photograph there. They acquired some temperatures down to a depth of just 20 meters on the Khumbu Glacier in Nepal in 1975. And they found that the top part of their profile was cold ice. It was well below the melting point. And then below that depth, the ice was presumed to be warm, but only really to a depth of about 20 meters. And these glaciers are hundreds of meters thick. So that's a big gap in our knowledge at the moment. The second area where we don't really have sufficient understanding is the effect of these large glacial lakes you can see in the bottom right of the slide. And these have started to develop at the tongues of many of these glaciers, at the termini of many of these glaciers. And they have a habit of absorbing lots of solar radiation, transmitting that through into the ice front and enhancing melt. And we've seen within the literature, the quote that you can see there from Owen King, that shows us that glaciers with lakes are losing mass at a much more rapid rate than those that don't have them. So that brings us really to the two questions that Alex and I are currently working on. The first one is, how warm is Himalayan glacier ice? There's really very little data. Those 1975 data were, until recently, the best data that we had. And then the second question, which is what Alex is working on, is what is the effect of the glacial lakes that are developing at the termini of many of these glaciers? So we'll just focus first on the warmth or the temperature of the glacier ice. So it's that question really that we set out to try and address with the Everdrill project. And as the name suggests, we were working in the Everest region and we were trying to drill into the ice. And what we wanted to do was get to a depth which exceeded that of the Japanese expedition, so that we could actively measure the ice temperatures throughout the year and be able to gain an understanding really of how close the ice is to the melting point. So is a 1 degree change in atmospheric temperature really going to make much difference to these glaciers? The answer is probably not if they're at minus 10 degrees Celsius, but it's going to have a big effect if they're already very close to that melting point. So we had a setup like you can see here in the image. The photograph is on the left and the interpretation is on the right. And you can see that we had this, pump and burner operation at the core of our method. This was kindly provided by the organization Glacier, which many of you may be familiar with as providing pressure washers. And their pump and burner really were just an industrial pressure washer, adapted for use at high elevation. And that was being fed by water that we were extracting from this supraglacial pond. So this is just a pond of meltwater which is sitting on the surface of the glacier. And we could pump that water through and into the pump and into the burner. And hey presto, we've got water which is heated and it's at pressure. And if we put the heated pressurized water through a nozzle, which has a very, very small orifice on the end, we can cut our way down through the ice as well as melt it at the same time. And we can drill then as far down into the ice as the length of the drill spool that we have. And we took 200 meters worth of drill spool with the aim of drilling 200 meters into the interior of the Khumbu Glacier. And so you'll see now, as we play the video, the setup that we had, and I can just talk you through a few of the features. You'll be able to see as the video starts that we're taking the water from a large supraglacial pond. This is a little Honda pump which is working its socks off to get the water from the supraglacial pond up through this 15 meters worth of pipe and into the settling tank that you can see at the top. That's an IBC, we'll call it. And that can hold 1,000 liters. So we're pumping water here at a rate of about 15 liters every minute, something of that sort of order. And there's a filter on that pump and that hose so that we can take out any large clasts and the fine sediment can just settle out in that IBC container. Now you can see that we're working here on a very harsh debris covered surface. This is, believe it or not, this is the surface of the Khumbu Glacier. So it's a glacier which has very thick ice and it's transporting on the surface these huge rocks that have come down in avalanche events. And you can see here the Glacier setup that we have. That's the burner at the back, which is running on diesel. And it's heating our water to something around 40 degrees Celsius, which really, you know, it's lukewarm at best when you compare it to the sorts of temperatures that we get at sea level. But this equipment was really, really working at its maximum limit. We did well actually just to get the equipment started after it had been in storage. And so that lukewarm pressurized water is then forced along this pressure hose and around the hose, which is on the drill spool you can see there. We've got 200 meters worth of hose that is actually on that spool. So that's the maximum depth that we can drill into the glacier. And it comes off of the spool again, then down through the rest of the hose. You can see a couple of markers on the hose, yellow markers just going off the bottom of the screen that indicate the length of hose that's disappeared into the glacier. And there's another white marker there just going over Evan's shoulder. And on the end of that hose, that's now about 15 meters into the interior of the glacier at this point, there's a drill stem, which is 3 meters worth of steel rod with a very, very small nozzle on the end, which is forcing the water through at extreme pressure. And so you can there see the borehole that we've produced at this location. It's maybe got about 6 inches diameter, something like that. And the meltwater, which is spilling back out as we've melted our way down. And then within that borehole, once we pull the hose back out at the end, we're left then with this very clean hole. And we can instrument that hole with exactly whatever instrumentation we want, which for our case was a thermistor string, which can then tell us, once that thermistor string has frozen back into the hole, it can tell us about the temperatures of the surrounding ice. So it takes a little bit of time to get back in equilibrium with the surrounding ice, but then it can tell us about the temperatures of the ice through that ice column at the specific locations at which we're working. So I think there was a link there in the chat to the methodological setup that we had. And I think given the fact that it is quite a novel setup, and as far as I know, the only time this sort of thing has been deployed at this sort of elevation, if you're interested in reading more about the challenges that we had to get that working, that's a good link to follow. So on the left of this slide, there's an image that's showing us getting one of the holes started. But one of the things that I just wanted to emphasize about this work was that it was strongly in collaboration with Kathmandu University. And the researcher that's in the middle of the image there is Dawa Sherpa, who was born in one of the villages, Kumjung, which is just down from where we were working at this site. And he was also doing a glaciology master's at Kathmandu University. So it was a highly collaborative project, which had a lot of knowledge transfer in both directions, worked in a very satisfactory sense from that point of view. On the right now of this slide, you can see the many different boreholes that we attempted, and some of them successfully completed up the length of the Khumbu Glacier, which is in the middle of that figure. It's panel B that you can see there. And you can see that we had 5 sites, site 1 down towards the terminus, site 2 about halfway up the ablation area of the glacier, and then site 3, which was near to Everest Base Camp. That's where we expected the thickest ice to be, and also the coldest ice, because it is still at very high elevation up at site 3. And you can see for each of the breakout panels, the sorts of depths of holes that we managed to achieve. So at site 1 in 2017, we had our first borehole at 31 meters. And I remember we went back to the lodge that night and we were very, very pleased with ourselves. And we tweeted to the world that we were the first team to have managed to drill through the Khumbu Glacier all the way to the bed. And then the next morning we went out and we moved our borehole about 5 meters to the left, and we drilled to a depth of 46 meters. So we therefore instantly proved ourselves wrong, that we hadn't got to the bed at all. And who knows even if we got to the bed at 46 meters at this location. So from site 1, we went to site 2. We drilled many holes at site 2, but we kept hitting the debris layer, so we couldn't get through because we're just using water at pressure, so we couldn't really cut through the rock debris that was within the glacier at that point. But at site 3, we drilled to a depth of 155 meters at our first attempt. So we were very pleased with that hole, and we instrumented that fully with some temperature sensors that I'll just show you the results from in the next slide. Just to complete this slide, site 4 and site 5 were from 2018. We went back the year after, and the maximum depth that we drilled to there was at borehole 4 at site number 4, where we got to a depth of over 190 meters, and we instrumented that too. But I think some of the most relevant data here to just emphasize the story come from site 3, which is, as I say, the highest of our sites and where we would expect the coldest ice to be. And so these are the deep ice temperatures that we recorded. Just to walk gently through this slide then, our naming convention for each of the thermistors has the site number, which is S3, and then the number which comes after the underscore is the depth below the surface that each of these thermistors sits. So the first one, 4.7, that's 4.7 meters beneath the surface. And that yellow color you can probably see is the only one that doesn't show a relatively horizontal pattern in terms of its temperature. And that's because it's sitting so close to the surface that it's actually being influenced by the seasonal air temperatures. So it has a trend which is basically controlled by the air temperatures around. But once you get deeper than about 20 meters, that seasonal effect disappears and we can see the steady state ice temperatures. And what we see then is that the coldest ice that we have been able to measure is actually about minus 3.3 degrees. And that was towards the surface of the glacier at a depth of 24.6 meters. And from that point, it gets warmer and warmer and warmer as we go down through the ice column. And that's exactly what we would expect as glaciologists. Ice is a very good insulator, very good thermal insulator. So as we go into thicker and thicker ice, then we expect the temperatures to increase. But we certainly did not expect for our coldest temperature to be just minus 3.3 degrees, which indicates that this glacier is already very, very close to the melting point. And you can see those data then plotted up, exactly the same data, but plotted slightly differently. So you can see that thermal gradient as we go down through the ice column. We're getting warmer and warmer ice. And you can imagine that if we were able to drill another 200 to 250 meters, we would intercept this dashed line on the right-hand side, which is actually the pressure melting point of ice, such that even around Everest Base Camp, our highest point in the ablation area, you would expect to see some ice within the glacier that is already sitting at the melting point. And so if you put these data together and you take a cross-section through the glacier, we can join some of the dots and we can assume that there's this cold temperate transition surface, the CTS, that defines the warm ice below and the cold ice above. And roughly calculated, we get about 56% of the ablation area actually sitting at the melting point already. And so a minimum temperature of minus 3.3 degrees. We've got cold ice, which is sitting on top of warm ice. And perhaps most relevant, we have ice, which is already 2 degrees warmer than the mean annual air temperature, which indicates to us that this glacier is already far out of equilibrium with climate. And a small climatic perturbation may just tip this glacier over to a point where it becomes into runaway recession. And if we go back to the data from 1975, we drilled as close to that site as we possibly could. And our data indicate that over that period, over about 43 years, the ice has warmed by 2 to 3 degrees. So we have fairly definitive evidence that the climatic changes we're seeing in this region are translating through into ice temperatures too. Just to talk briefly about the second question that we've got then, and this is really about the influence of these glacial lakes on how glaciers are going to evolve into the future in coming decades. And this is really Alex Scoffield's PhD work, and these are Alex's slides that's just put together to really summarize what it is that she's trying to achieve. And we're interested here in, if we have an idea of the future evolution of these lakes, can we build some of the parameters that these lakes exhibit into our numerical models to simulate the effect that they'll have on first melt, but secondly also the dynamics of the glacier, if they can draw some of the ice down and into those lake basins that perhaps a land terminating glacier would not be able to do. And the literature shows us that at the moment we have hundreds of these glacial lakes already across this third pole region. If we fast forward some of the data, we can have a fairly good prediction as to where these lakes are going to develop into the future. And those hundreds turn into thousands and maybe even tens of thousands of lakes by 2100. And so ultimately what Alex is trying to do is simulate the effect of these lakes on future glacier evolution. But in order to be able to do that, in a similar way to the ice temperatures, she needs to understand what the lake temperatures are at the moment, what the thermal regime is likely to be, and how that changes throughout the glacier melt season. And if she can do this, then we'll actually be able to derive some of the first measurements that we have on lakes and lake thermal regimes for this region of the world. There's really very few observations at the moment. If we can parameterize these models a bit more robustly, then we can really start to reduce those uncertainty bounds a lot better. There are some data from Patagonia that indicate that glacial lakes, as you can see on the right-hand side here, are quite reasonably stratified so that we can have some element of prediction about what we might expect to find in the Himalaya, but with very few existing measurements to be able to properly parameterize these models. There's indication that cold water is actually trapped at the base of these lakes because the water is very heavily sediment laden. And so therefore the density of that water is actually a key control here. And how it evolves through the different seasons is almost entirely unknown for the region that we're working in. So that's really what we're setting out to do in May, on May the 2nd actually, which is getting actually somewhat close to departure time. And we're heading to Chulagi Lake in Nepal, which is a lake that has developed very rapidly since the 1970s, but it's relatively accessible. You can see there from the image on the top of the slide. This is somewhere where we can feasibly deploy a boat from the lake margin and go and instrument the lake with some of the sensors that we want. It's hosted by this heavily debris covered Chulagi Glacier, you can see in the bottom right, which is very characteristic of the sorts of glaciers that we see elsewhere in this region. So we're very hopeful that if we can characterize this glacial lake, then it should be applicable elsewhere. And we're leaning on a few different data sets that have already been collected for this lake that indicate the sort of methodological strategy that we're employing, that I'll just come on to shortly, should be successful. So we're trying to answer the questions, how do lake temperature change with increasing depth and over the melt season? And also, what does the bathymetry of the lake look like, particularly for the submerged part of the glacier? So we're going to deploy a boat on the surface of this glacier. There's myself and Alex in the illustration. And we're going to drop a thermistor string into the lake, which is going to be weighed down with a sandbag and kept at the surface in position by a buoy. And we're going to hope, beyond hope, that over 6 months, this thermistor string is not taken out by icebergs, and we'll be able to go back in October and collect all of our sensors in and reconstruct the thermal profile over that 6-month period. And we're going to be using some tiny tag and eye button sensors to be able to do that and try and replicate the work from Patagonia that has really been quite groundbreaking in the data that it's been able to present. And we're also then going to deploy for our second question a sonar, which should be able to nicely image what the lake bottom topography looks like and what the submerged part of the glacier looks like, because the geometry of this lake is really going to be key in terms of being able to project forward how it's going to influence glacier melt. So that's our plan. That's what we're targeting. Whether it comes off, well, we'll find out. I can report back to you in a few months how successful we were. But overall, if we can collect this 6-month data set that we're aiming for, it will be the first of its kind. We'll have an existing ice dynamical model, which these data can go directly into. And we should then be able to reduce that uncertainty gap that we're talking about to make a much more robust measurement of how glaciers will change into the future. Lastly then, just a couple of slides on working with the communities and the sort of work that we've done over the last few years to be able to talk about some of these research findings. And one of the nicest organizational events that I've been involved with is this Walk the Talk field conference, where a couple of our researchers that you can see here on this slide, so Scott is second from the left on the lower group of people, and Katie is second from the right on that lower group of people, walked on successive days through a group of these villages where we've been working and gave a series of presentations to be able to talk about the sorts of temperatures that we'd found within the ice and what that might mean for future Himalayan glacier evolution. And then in addition to that, we've done a lot of our own outreach activities. And you can see here some of the more interesting and exciting sorts of activities that we've put on. Some VR headsets here with the local villagers, being able to visualize some of these future scenarios for themselves. Going into schools and working with the youngsters to talk about climate change and the landscapes that they can expect to see in coming decades, and even doing some hydrological experiments with a mocked up glacier and some syringes and some coloured water, again with the local villagers so that they can understand where the water is coming from and how likely it is to change in future years. And then we've also produced a series of infographics. This is a good example here. That we've had translated into several different languages. So again, people in the communities around where we're working can understand some of the findings of the projects that were being undertaken here. And I think we'll be able to distribute an electronic version of this after the presentation has ended. So just to conclude then with some key points, I think hopefully it should come across quite clearly that these glaciers are in the Himalaya and the third pole more generally are responding to climatic changes at a rate that is beyond historic precedent, certainly anything that we have any hope of being able to measure. The impacts on those communities that we've just seen are likely to be profound because they're very dependent on this meltwater for irrigation and sanitation and hydropower. We have measured that the ice is already warmer than the mean annual air temperature, so it's quite far out of equilibrium. And it means these glaciers are pretty vulnerable to even minor atmospheric warming going forwards. And then one of the biggest outstanding unknowns is still the effect of these glacial lakes on future evolution. But this is something that Alex and I are actively working on to address. And hopefully we can update you in a few months as to the success of our field visit to Tulagi. So I'll end there. Thanks very much for listening, and I look forward to a bit of discussion and any questions you might have.
Thank you so much, Duncan. That was really interesting, but also quite concerning as well, I think. Just give you a moment to grab a drink of water or catch your breath. And just a reminder to our audience, if you would like to post a question, please do so using the Q&A facility. And if you like one of the questions that has already been posted, then please feel free to upvote that question so that it gets to the top of our list, and we will try and answer as many questions as we possibly can. Right, Duncan, I've got a question actually to start off with, which is, I know we talked at the beginning about the importance of glaciers for the downstream communities and in terms of providing meltwater for water supply. But do the changes that you see in the mountain regions impact on the downstream communities in other ways as well?
Yeah, they do, definitely, Martin. I think what we're seeing is that as these areas thaw, so for decades they've been frozen solid, which is a really good way of keeping everything stable. As they thaw, they become more dynamic. There's, even on a very fine scale, there's more meltwater between sediment crystals that can activate slopes that have previously been solid. So we're observing an increase in the number of landslides, for example, and we're observing an increase in the number of ice avalanche events. And you may be familiar with some of the ones that have been in the news within the last couple of years, where we've even seen whole sections of glaciers shearing off from the upper part of the glacier. The theory being that as we warm the ice, we increase the amount of meltwater which is at the bedrock ice interface, and lubricating that interface such that the glacier can actually just slip off and create these huge ice avalanches going down the valley. And there's some social media clips that people have caught of these catastrophic events in which some people have unfortunately lost their lives. And then the other main hazard that comes with these glaciers receding is very much as we saw in the case of Tulagi there, the development of these large glacial lakes, which generally speaking, I think they're probably quite stable because they've now existed for several decades and they've experienced a major 2015 earthquake. So real, seismic stress being applied on these lakes. And you might hypothesize that if they were likely to fail, then they would have failed in that Gorka earthquake. But nevertheless, people who are living directly beneath these vast reservoirs of water are rightly concerned that at some point those moraine dams may fail. And we have seen historically in the third pole and in the Himalaya in particular, a series of catastrophic glacial lake outburst events. So even if it doesn't happen, the mental strain that it puts on people who are living in those regions must be quite significant, I think.
Very, very concerning. And another question that I had, Duncan, was how representative is what you're seeing in the Himalayas and in the glaciers that you're studying in the Himalayas? How representative is that to other parts of the world, other glacial fields around the world?
I think it's quite tricky to extrapolate much further afield beyond. I think we would say that we're quite confident that the glaciers that we're looking at in the field are representative of glaciers elsewhere in Nepal. They tend to have similar elevation range, starting and finishing range. They tend to be debris covered. They tend to be driven by the same climatic conditions. I think the further you get from that point, the less confidence you have that those sorts of data would be replicated. But I think the key part to answering that question is the don't know bit. And it really emphasizes for high altitude glaciers, like in the Andes, for example, would be the natural comparator. There's no equivalent data. The data that we acquired in the Himalaya were the first of their kind there. And if we were to repeat that project in the Peruvian Andes, for example, they would be the first of their kind there. So if we want to properly forecast the future evolution of these glaciers, we need to get into these environments and into these very high elevation zones and repeat these sorts of measurements.
Thank you. Right. So I'll just have a look at the questions that have been posted then, Duncan. So there's a question here from Ishfaq Malik. Thank you, Ishfaq, for your question, which is most of the Himalayan glaciers are shrinking, but some parts of the Himalayas showed positive glacier budgets known as Karakoram anomaly. I hope I pronounced that correctly.
Yeah,
Could you please explain the reasons for the existence of the Karakoram anomaly?
Yeah, hi Ishfaq. I mean, we've seen over the last 20 to 30 years that the Karakoram has been really the one region of the world which has managed to avoid this real rapid rate of recession. And Ishfaq's absolutely right. Those blue colors that we saw on one of the slides indicates these glaciers have been either stable or slightly positive in terms of their mass balance. And we understand that reasonably well now. The climate over in the Karakoram is very much driven by the westerly winds, whereas the climate, as you go further around towards the east through India and into Nepal and Bhutan, where we saw most of those reds, is really driven by the monsoon period. So their summer accumulation types, actually during the summer, that's when they get their snowfall. The glaciers in the Karakoram with the westerly winds, that they gain their mass during the winter. And we've seen in the data, in the climate data, that the strengthening of the westerly winds has also seen a consistent increase in the snowfall in that specific region. So that's the driver of the positive changes that we've seen. But the most recent data that have come out within the last 12 months show quite clearly that that period of positive balance is well and truly over. And we anticipate that that region will now also undergo the same sort of rapid changes in terms of negative mass balance that we've seen elsewhere across the range. Great question.
Great, thank you. Question, an anonymous question here, do we know how big the impact of debris on the glacier is in that region in terms of the temperatures it has underneath? i.e., is the thickness of debris acting as an insulator in that region, or is it working in the opposite way and heats it up?
Yeah, that's also a good question. And the answer is it depends on how thick the debris is. And so there's certainly a zone in the glacier where you've come through the accumulation area to lower elevations and the debris is just starting to appear as you go down in elevation profile. And where you've got that thin debris cover that may be only a centimeter thick or something like that, and maybe it's dust actually rather than clasts, then that's the area where we expect to see the debris enhancing the melt, because it's a thin debris layer that darkens the surface. It can absorb more solar radiation, and that solar radiation is very effectively transmitted through into the ice within that zone. And so that zone may persist for, I'm guessing, and it will change from glacier to glacier, but maybe like 500 meters to a kilometer, something like that, before you get to the thicker debris, where it's now maybe 10 centimeters thick or something like that, at which point it becomes an effective insulator. And as you then go further down towards the terminus of these glaciers, you might find debris which is several meters thick. And that is a really effective thermal blanket for the glacier ice. So within that zone, once you've gone beyond a few centimeters, maybe 5 centimeters thick, then the debris will act as an insulator, and it will protect the ice from incoming solar radiation. The extent to which we properly understand that is, I would say, we're pretty advanced. We've got lots of thermal profile data that people have taken pits into the debris. They've put thermistors into the debris, and you can really measure. Then you put the debris back and you recreate the original situation. You can measure what the thermal transmissivity is through that layer. There's some questions about moisture and airspace, but I think we can pretty well model what the effect is. One interesting unknown, though, is that if you look on a very broad scale and you look at the mass balances of glaciers with debris on, and you look at mass balances of nearby glaciers without any debris on, they show remarkably comparable mass losses. So even though theoretically a large part of the glacier might be covered in this thick debris blanket that's supposed to protect it, the observational data still suggest that clean ice glaciers are losing mass at a comparable rate. And the jury in the literature is still very much out on that point. Something that as a community, we're really still trying to get to grips with a little bit.
Great, thank you. Another anonymous question here. During your time researching this area, have there been any glacial lake outburst floods? Do you think that these will increase over time as melting continues?
Yeah, so I've been working there since 2003, and there've been a couple of relatively small events that have impacted on maybe a couple of villages. And they've come mostly from water which is trapped within the glaciers, rather than the classic glacial lake situation that we saw with Tulagi, where you've got a large lake at the terminus of the glacier. So thankfully, there haven't been any catastrophic large glacial lake outburst floods in this region while I've been working there. There's been several that preceded my time, and you can still see the flood scars, and you can visit the moraines where you can see this incision notch where the water has poured out when it's failed. The couple that I have not witnessed directly, but been there very soon after, are these ones which are really very difficult to predict, where the water is, for some reason, the meltwater is blocked within the glacier hydrological system. And it sits there undetected, and then that blockage for some reason then is cleared. The water can burst out and it can pop out anywhere within the moraine system. It's very difficult to predict, but it can impact directly on the villages, which tend to be in the valley bottoms, because that's where the most fertile area to live is. So yes and no is the answer to that question. And I see my light's just gone off, so I hope you can still see me.
I'm slowly disappearing into the dark here as well. Right, some fairly quick fire practical questions here for you, Duncan. The first one is, how do you choose the sites for your boreholes? I find it interesting that some places seem to be quite close together. Is there a specific reason for this?
Yeah, good question. One of the primary controls on our field sites is proximity to a water source, because of the method that we're using. So we couldn't stray too far from the supraglacial ponds that were on the surface of the glacier. Now, there are many to choose from, so we weren't totally restricted, but we also needed to be able to access the ice. And so when you get down towards the terminus, and you might have 3 meters of vertical debris before you get to the ice, we were looking for areas where there was some exposures, so we could just move a foot of debris, something like that, and then be able to penetrate through into the glacier. So the first control was proximity to a water source, and the second control was how quickly we could penetrate into that ice.
Thank you. Next question, how big is the team that works on such field trips, and is it hard to obtain funding for such work?
For the drilling project, we had a team of, depending on the season, anywhere between 6 and 9 researchers, which included a couple of academics, a couple of postdocs, a couple of PhD students, and then maybe a couple of people around the periphery who were collecting data that was related to the project, if not directly on that project. And then a Nepalese team of maybe at least the same number who were running the camp that keeps us sustained, because we're camping on the glacier surface ourselves. And there needs to be food to be brought in and brought out and prepared, and all the unsavory things that you don't want to have to think about, but waste and so on and so forth. So yeah, at least the same sort of number of Nepalese involved in that. And I forgot the second part of the question, Martin.
Sorry, let me just go
size of the team.
Find it.
Oh, and is it difficult to get research funding?
Yes.
It's difficult to get research funding. It really is. Yeah. I think with this sort of project, where we have had success is often the simplicity of what we're trying to do. And I remember when I came up with the idea for the drilling project, I actually explained it to me grandma, who was 92 years old, and she got it. She totally got it. It's like, we want to drill some holes into the ice, and then we want to put some temperature sensors in to measure how warm it is. And so when you can convey things that's clearly in a grant application, I think you've already won half of the battle. But as with everybody else, Martin, I'm sure you'll understand too, it's really hard to get research funding these days. Indeed
it is, yeah. Right, question on water quality here, Duncan. The melting water in the area, is it fresh? Or could it be used with, say, little treatment, or is it salty like ocean water?
It's fresh water, so it should be at the source. It should be almost as pure as you can get. Its use in terms of being able to consume, for example, is slightly compromised by the fact that there's a heavy sediment load within it, because as the glaciers move, they cut down through the landscape and they're eroding sediment all of the time. And a lot of that sediment gets locked up within the glacier itself. And as it melts, it releases the water with the sediment. And so you get what we'll call glacial flour. They're very fine shards of sediment within the water, which if you're not accustomed to drinking it, it will make you very poorly very quickly. So it's fresh water. It can definitely be used. It's very, very widely used for irrigation and for hydropower and non-consumption across the range. But in parts of the range, like the chap in Pakistan at the very start, they do directly drink that water as well. They're used to drinking it, they're used to consuming it, and their bodies are well adapted for it.
Thank you. Follow-up question here from Marina Rupp. Thank you, Marina, for your question. So this is a follow-up to the Karakoram questions that you had earlier. You've said that the Karakoram is going to face negative mass balance soon as well. Do you think that the focus should be put on this area research-wise then, so this process can be followed closely and we get a better understanding of what happens at such a tipping point of going into a negative mass balance?
Yeah, good question, Marina, and hi. I mean, the Karakoram is a fascinating region in its own right, and I think there definitely should be more research funding put towards understanding this tipping point, and we can actually observe it as we go through time. I think there's an argument that, given that the Karakoram is at the early stages of, well, what we anticipate, but there's still quite a lot of uncertainty around that, but what we anticipate is going to be a period of negative mass balance. Then it will be interesting to see how that unfolds. But I think the most pressing problems are perhaps elsewhere. We do know that the Indus, which eventually the Karakoram glaciers drain into, is particularly important in terms of glacier-fed meltwater. So in terms of how that's going to play out over the next 30, 40, 50 years, it is definitely one that we need to have as much information as early as we can. So I think it's a bit of a sketchy answer. I'm sitting on the fence there. Probably present problems more enhanced somewhere else. But I think the Karakoram is definitely one that we need to get on top of as quickly as we can.
Okay, thank you. Final question in the Q&A or posted live is from Ian Crossley. And Ian asks, do satellite images help correlate glacier loss and terminal lake growth and act as a surrogate for bringing on site?
And act as a surrogate for being on site?
Yeah, for being on site.
Yeah. Yes, they do, very much so. They correlate very nicely. We can see the direct connection between glacier area changes, but moreover glacier volumetric changes, because we can measure the elevations of the glaciers very reliably now, and the growth of these glacial lakes. So I think we can use those measurements on a broad scale to say a lot about how the glaciers are changing, and we can make some quite broad remarks about how they're likely to evolve in the future. I think what we try to add here in the School of Geography is that if you want to look at an individual glacier, then you have an individual glacier in one catchment and it can very, very easily behave differently to the glacier in the adjacent catchment. And so to understand individual glacier processes and to understand how an individual glacier is going to impact on the people who are living downstream, then the process-based measurements that we're attempting to undertake in the spring, but also we've done previously, I think that's where this field-based element is really, really critical.
Brilliant. Thank you, Duncan. So just one final question, if I may. This is a pre-submitted question. If you won the scientific lottery, what would you spend the money on? Would it help you to answer any of the outstanding research questions that you have?
Well, I'd like to know where I can buy a ticket for the scientific lottery, as I'm sure you would too, Martin. If we were to win it, then I think it would be really useful to be able to design some robots that actually allowed us to get into the interior of the glaciers through some meltwater portals that we see on the glacier surfaces, but we're just too scared to actually put ourselves into. So I'm really intrigued by the work of organizations like Boston Dynamics, who've produced the RoboDog, which unfortunately it costs £180,000 to buy. So I don't have that loose change in my pocket to get one. But, you know, we've got a fantastic robotics team here at the University of Leeds, and it would be really, really exciting to have some research with the robotics team to be able to design some autonomous robotic sensors that we could put into the portals, and they could go along the portals and they could work out when they're going to get wet and go to some sort of robot that can swim and measure. They can take profiles of what the internal channels look like and how much water is in there, how fast it's flowing, whether it is clean, whether it freezes up, whether these lakes that are stored within the glaciers actually exist and we can observe them for the first time. So I think that's the way then you get this distributed vision of what's going on inside the glacier, rather than our point-based measurements that come in from the surface, valuable as they are. But I think an internal glacier robot is kind of my dream.
Yeah, fantastic. Right, well, that exhausts the question bank, Duncan. All it remains for me to do now is to say thank you once again. That was a fascinating presentation. And yeah, it certainly increased my awareness and knowledge of what is going on in glaciers around the world, and particularly in the third pole. So thank you very much for your time today.
Thanks for having me, Martin. Thanks.
Okay, so that brings us almost to the end of the 4 presentations that we've had as the Meet the Researchers series focusing on water. I hope that over the last 3 weeks, what we've been able to do is demonstrate some of the scales and some of the locations right around the world where we engage in actually undertaking water research, but also really the kind of enormous variety of the work that we do in water at Leeds, at the University of Leeds here. I think more than anything, what Water at Leeds does is it brings people together within the university to start to have the discussions and to start to define and explore some of the research questions and some of the challenges around water that you've heard about over the last 3 weeks. But Water at Leeds is more than just being an internal network of people. Obviously, it's also crucial that we engage externally as well. and that we start to partner with different organisations right around the world, so whether that be other universities, governments, NGOs, commercial organisations. We engage with everybody where it makes sense for us to do so, and to actually inform our research and to begin to answer some of this multitude of questions. And that really, in a nutshell, is what Water at Leeds is all about. If you'd like to find out more about Water at Leeds, then what I'd invite you to do is to have a look at the website. I can see that Megan has just posted a link to the website in the chat here. So if you want to know more, please click on the link and check out a bit more about the website. And I'm sure that the advancement team will be happy to answer or to pass on any other questions that you might have. Apart from that, all it remains for me to do is to thank you all for your attention today. And also for your interest and attention over the last 3 weeks. Before we end, just one more thing for me to do, which is to invite you, please, when you close the Zoom link, there will be a form to provide some feedback from today's webinar. We very much value your feedback, so if you could just take a couple of minutes to do that, that would be fantastic. Once again, from me, thank you very much, and thank you for your interest in attending today and this webinar series. Thank you, and good evening.